so some will work better than others. In certain scenarios, some won't. So this is something you're gonna have to work through in your homework one to decide which activation is going to work the best. Yeah. Cool. So once you've predicted your outputs through your forward pass, you want to initialize your, or you want to compute your loss function with your predicted outputs against your ground truth labels. Now, depending on the task at hand, you could do, if you're doing regression, you might use losses like mean squared error, root mean squared error, things like that. If you're doing classification, chances are you'll be using cross entropy or tail divergence. We'll learn more about all this, or Professor Bixia will go over all this a little later on in the semester. Here, just an example, we're going to define a MSE loss. So this is going to be for a regression task, but if you're doing classification, you would do cross entropy. So you initialize your criterion first, and then in your loop where you're looping through your batches of data, you're going to compute your loss by calling this function over here. So this is going to be the outputs from your forward pass, and then this is going to be your ground truth labels. And so loss will be the MSE loss between these two. Once you've computed your loss, you want to do a back propagation with that loss. You do so by calling loss.backward. We haven't gone through back propagation in lectures yet, but essentially what it's doing is it's computing the gradient of the loss with respect to your model weights. And then you sort of have to do this layer by layer by working backwards, hence the name backprop. So once you compute your error, you can use that to compute the gradient of the error with respect to the weight of this layer. And then you would keep going by passing along the gradient of the loss with respect to your output from this layer. And then as you work backwards, eventually the internet will have access to the gradients of each parameter. And then using those gradients, you can then do your gradient step. So loss.backward computes the gradient. All those gradients are stored inside the parameters. We'll see this in a bit, but loss.backward computes all the gradients. Right, so once the gradient's computed, you want to take your quote-unquote update step. So this is where you use that gradient to compute or to update your weights in your model. So this is typically done this is typically done at the end of a batch where sorry, not at the batch, at the end of every batch where you want to update your parameters. The most standard one everyone is familiar with is probably gradient descent, where you take a step in the negative direction of your gradient. So if this is your current model parameter at time step t, this is the gradient of the loss function with respect to your parameters, where theta is your parameter. Alpha here represents a sort of like a step size learning rate. And then you want to take a step in the negative gradient. So your current weight minus your step size times the gradient of the loss with respect to your parameters. And that'll be your parameters for the next time step. So gradient descent is the most standard update rule. You're gonna, as you work throughout this course, you're gonna be introduced to different optimizers, things like RMS prop, Adagrad. I'm sure a lot of you guys know Adam already. These are more, the update step is gonna be a little more complex for these, but Professor will go through all this in lectures. So here's how you would initialize your optimizer. For here, we're doing a standard, stochastic gradient descent. And then you want to pass in your model parameters as well as define the initial learning rate. Then you would do optimizer.step is the update step. Optimizer.zeroGrad is what clears the gradient in your optimizer.zeroGrad clears the gradients that is stored inside your parameters right now, because the gradient is essentially being accumulated. And so at the end of every update, you want to clear. So this usually comes at the start, at the very front of your loop. And then at the very end, you want to do optimizer.step. We'll go over this whole thing later on. I mentioned earlier that you can check the gradients by doing this. So this is your initialized model. If you do if you loop through all your model's parameters, you can print their gradients by accessing the .grad attribute. So all your gradients are stored in .grad. If you call optimizer.0grad, that clears everything. If you do loss.backward, that recomputes the new gradients for this iteration. So it's essential that you call optimizer.0grad at the start of your loop, or else your gradients just going to keep accumulating and that'll fail. Right. Models also perform somewhat differently when they're in training mode versus eval mode. I'm not sure how familiar everyone is with all this, but I'm sure our professor will go through these in lectures. So what dropout does is essentially it sort of switches off some of the neurons, or which is equivalent to setting some of the output to 0. And this is to prevent overfitting. So this is a regularization technique. During training, we want to do that so that it doesn't overfit. But during eval, which is when you're trying to evaluate your model, you don't want this to happen, right? You want all the information possible. But similar for batch norm. In batch norm, you compute the mean and variance of the entire batch, and then you normalize your whatever you're passing through your model. But now, it's important that the mean and variance you use is from your training, not from your evaluation. So when you're doing evaluation, you don't want to use the mean and variance from your evaluation step, because that would sort of be like cheating, right? You want the model to act the same when it's training, or when you're evaluating it as it was trained, or else it would be cheating, right? So you want the model to behave the same. So what batch norm does during eval is it stores the mean and variance while it was training, and it uses those values during eval. It doesn't recompute the mean and variance during eval. And data augmentation, another regularization technique, but essentially you're sort of increasing the diversity of your data set. You don't do this during eval, you only do this during training. Any questions? Cool.
Oh, we got a question.
Yeah.
Will these be tested on quiz?
I think some of them will, maybe not this week.
We have two kinds of quizzes, if you have noticed. One's going to be like the quiz that's going to cover the lecture content that professor covered in class, and one will be specific to homework part 1, the homework part 1s and 2s. So this might come in the homework quizzes and not like the weekly quiz, which takes in the lecture content. There might be some overlap because the professor covers content in the lecture, which is used in the homeworks. So yeah.
There's a homework quiz. I thought there was one quiz per meeting.
The homework quiz is to be submitted before the early submission deadline. So the deadline for both is not the same.
Okay.
Yeah, so the weekly quiz this week won't include any of this because professor hasn't gone through any of this in lecture. So we're sort of jumping ahead here. But these are all really common techniques that you'll use as you're doing your MLP. And you'll definitely use it in homework 1. Yeah. So yeah, model.train to set it into train mode, model.eval to set it into eval mode. This causes the model to sort of behave differently. So it's important that you call the right one when you're doing train versus evaluation. A last note is that your model and your data has to be on the same device. By that device as in GPU versus CPU. So if you do have a GPU available, if you call this function, or not function, this function, push.CUDA is available, this will return true if you have a GPU available. If not, it will return CPU. And it's important that you initialize this device, and then you want to move your model and your data to that device so that they're on the same device. If they're on different devices, your code will throw an error. So model, move to device, your input to device, your ground truth labels to device, so that you're able to call something like this. If they're on different devices, this will fail. Cool. Finally, to put everything together, this is
I think
sort of.
You got a question?
Yeah.
We have to do that step again if we're ever changing our architecture and rerunning one, right?
If you're changing your architecture, yeah. So whenever you initialize your model, you probably want to move it to device, unless there's something you want to do. So you would probably move it to your GPU, and then if for whatever reason you need it in your CPU, you would have to move it back to CPU and then move it back to GPU again.
It's probably also worth noting that if you're using Collab or GCP or AWS, the GPUs you're given already have PyTorch installed with CUDA as its preference. So You can do that to check, of course, but realistically, they're going to be that way. But if you're doing it yourself, the default PyTorch library, if you're using pip, will give you the CPU one, and it will not utilize your graphic card if you do not set it manually. So be careful with that.
Yeah, so if you go on Colab right now, and then you selected a hardware accelerator as GPU, this will return CUDA. So this is another way for you to check if you have a GPU available. Any other questions?
Can you use some microphone or something because people in the back maybe not, we cannot hear you.
Is that working? No.
I don't think the microphone's working now. Even if you just, yeah.
Good.
Is that all right? Testing.
Is that
better, guys?
Sorry about that. Yeah, so just putting everything together, this is what your standard train one epoch would look like. You can definitely do more advanced things, but this is sort of the general procedure here you would go through. So again, firstly, you set your model to train. Again, this is so that your model behaves in train mode, I suppose. You also probably want to keep track of your loss during as you are training. This is for each epoch. So eventually we'll return the loss that has been accumulated per that epoch. You then loop through your batches. So if we're doing stochastic or not, if we're doing stochastic gradients, then you'll have batches, and then you loop through them by doing this by looping through your data loader. Optimizer at 0 grad sets the gradients to 0. You have to do this at the start of your loop, otherwise your gradient will accumulate and then your update state will fail. Moving your input and your ground truth labels to the correct device. If you have CUDA available, this will go to CUDA. Outside of this, you probably want to move your model to your device as well, but we didn't include it here. Then you do your forward propagation. Once you have your predicted outputs, you do your loss. You compute your loss with a predefined criterion. Just now we defined it at MSE, but that would depend on your task at hand. And they also perform slightly differently, so you can test a few out during homework. But you compute your loss with your predicted outputs from your forward propagation, with your ground truth labels, and then you call loss.backward to compute the gradients. Once you call loss.backward, you take your gradient set by doing optimizer.set, so that updates your weights, depending on what optimizer you have selected. And then finally, you accumulate your training loss, and then you return your training loss. This over here just divides your training loss by the number of batches, which depends on your batch size and the size of your data. So what we return eventually is your loss per batch. Any questions? Cool. Final note about, so we showed you the training code just now. Eval will look very similar to that, except you want to set model.eval rather than model.train. And then also you can speed things up. You can speed up your evaluation by doing with torch.inference mode. Essentially what this does is it lets PyTorch know that, I'm not updating any weights. You don't have to maintain a computation graph. So this saves computation, this saves memory, and this essentially speeds up your inference code. So when you're writing your eval function, make sure to do this to make your code faster. And then yeah, call model.eval when you're doing eval, call model.train when you're doing train. That's it for the slides. Any questions before we go into the notebook?
Any questions on Zoom? Doesn't look like. Okay, so since we don't have any questions, I would like to invite you all to open the collab exercise notebook that we have linked in Piazza Post 87. And it's basically, okay, we have a question. Oh, is this better? So if all of you have access to the collab notebook, it's basically the first part of the notebook. Okay, before that, just two reminders. A question about this was asked just before. So we have two kinds of quizzes that have already been released. First one is the weekly quiz, which was also released yesterday on Jan 19th, and the second one is homework 1 quiz. So the deadline for the homework 1 quiz is the early submission deadline for homework 1, and deadline for the weekly quiz is at the end of the week. So these are 2 different quizzes. Make sure that you attempt both of them and don't miss any of them. Okay, so this notebook, the first part of this notebook is going to have a lot of math behind what Sam just spoke about. So it's going to be, Sam just explained to you the theory and what actually goes on when you train an MLP. This first part of the notebook has all the mathematical equations and the explanations that you need in order to have a more detailed understanding of the mathematical foundations behind this. So please feel free to go through it and let us know if you have any questions. For now, we'll be jumping right into the part which is right here. Part 3, where we basically have a very simple MLP example, the MNIST digit classification example, which is considered as the hello world of deep learning, to put it very simply. And I would like all of you all to, so it's a very simple exercise, and it mostly follows along the slides that we just saw earlier. There are blanks in the exercises, which we would like all of you all to fill. And for that, you need to refer to the documentation, and we would strongly urge familiarizing yourself with the documentation, looking at the documentation and actually like extracting stuff from there to fill all these details. So the first part of the cell, if you see, it's just installing all the libraries that you need for running the content that follows. And after that, we have the data sets and data loaders, which I'm sure all of you must have seen in Recitation 0. Just by a show of hands, how many of you have been able to watch Recitation 0, I, J, and K, the data set and data loaders recitation? Okay, not many of you. So we would again strongly urge all of you to go through that before you start homework 1 part 2, because it's going to be really helpful for you to know and learn, and it'll really help you solve the first part of the data sets and the data loaders in that notebook for that particular homework. So if I have to just briefly go over that for now, what we have in the data sets and data loaders is essentially, like here, what you're doing is we're taking the loaded data where the features are of shape B into 1 into 28 into 28, where B is the batch size. And 1 is basically like the channel size because it's a grayscale image. And so essentially when we say that it is B into 1 into 28 into 28, we are saying that we have B images of 1 into 28 into 28 channels, right? So that is what we are doing here when we're loading the data. And we are using an MLP to flatten the images so that our data is of the shape B into 784, which is 28 into 28, basically. Yeah, this is where you create the data loaders. And you can run these cells to just visualize the kind of data that you have in your data set. If you're still following along, this is the section 5, which caters to, like, now we'll be going deeper into how we actually start building our model and the architecture. But before that, before deciding on the architecture that we want to build and the number of hidden layers that it will have and the input size and output size, we define all of this right here. The input size will be height into width, which we have obtained in the cell before this one. We have specified the hidden size as 1024, and the output size is going to be 10. One important thing to note here is that while we can always vary the size of our hidden layers, the size of the input and the output is obviously going to remain the same. So it's a very obvious fact, but when you actually do homework 1 part 2, you run into a lot of shape errors, and this is one of the most common ones where you have a shape mismatch because you're not matching your sizes of the hidden layer, or the hidden sizes and the input sizes and the output sizes well enough. So just keep that in mind. And yeah, so here's the first set of blanks. I think you just saw something very similar to this in the slides that Sam just shared. We would like you to go to the documentation, just look at how it is, and just fill in those, fill in the network. We have the torch.nn.sequential to sort of have a combination of different linear layers and activation layers. And when you look at the activation functions, you can look at all the different kinds of activation functions that are available in the documentation for PyTorch. There's ReLU, there's leaky ReLU, there's GELU, there's SILU, there's like tons of them. And you can see what sort of works best for your models. That is what you'll be doing in homework 1 part 2. You'll be seeing which kind of activation function leads to a better performance for your models. You'll be running ablations. So I think this is a good place to just get started, playing around with all of this. And also just one thing I'd quickly like to add here is you can also explore like building such kind of models in different shapes. By different shapes, I mean, like we say the architecture has an hourglass shape, or like it has like a diamond shape or a cylindrical shape. We basically create this shape by varying the size of the hidden layers. So if it's an hourglass, the first layer is wide, then it's narrow, and then it's wide again. If it's cylinder, all the layers are of the same width. And if it's diamond, then it's narrow at the top, it's wide, and then it's narrow again. So again, like different kinds of shapes of architectures provide different kind of results. You'll see when you run ablations for homework 1 part 2. So that is something you can play around with here as well. And yeah, and then the train function, we have filled most of the train function for you. There's some of it which we have left for you to fill. And yeah, just to sort of quickly go over it, I think Sam just already went over it, why we have and how we use model.train and model.eval. So since this is a train function, we are using model.train to enable parameters to be updated during backprop. And then we have the train loss variable, which is basically initialization for cumulative training loss across the entire training loop. And yeah, so the first thing that we do in the for loop is moving the data to device. And he just explained about the significance of CPU and GPU in that case. And then we run the forward pass, which is basically passing the flattening input images through the model so that we get the model's predictions. We then have to calculate the loss using models, outputs, and labels. That is the 2 blanks that you'll be filling in. I think it's very, yeah, I know the pizzas are here. I'll be finishing quickly. Don't worry. So yeah, so I think these 2 blanks are pretty easy for you to fill. We have comments over there, and we also have the slide deck that you can refer to. Next, the train loss plus equal to dash. That dash, what are we adding to the training losses? Does anybody have any idea? It's basically like we're accumulating the current batch loss to the overall training loss, right? So there's a dot item function that you might want to look into. And I think that will pretty much help you fill in that blank. Next, you zero the existing gradients, like of all the previously optimized tensor, so that you prevent the accumulation of gradients from previous batches. Then you calculate the gradient of the whole network using the loss dot dash. I think this dash again is very, I think you know by now what it is. basically to compute the gradients of the loss with respect to the model parameters. And not lastly, and then we step the optimizer to update the model parameters using the computed gradients. And lastly, we can compute the average training loss over the batches of the epoch, which is obviously what you will be returning right here. And then similarly, we have like the eval function pretty much set up for you. Yeah, now coming to this part, the optimizer and the cross entropy loss. We have provided an example of one optimizer, that's Adam. But I would really recommend going through all the entire list of optimizers and by yourself explore Adam, Adam W. There's Adam P. Adam P is not directly available on PyTorch, but we have. I'll talk about it in a few minutes. SGD and like several other optimizers that you will be using in your homework 1 part 2. So I think you should, this is a good place to, experiment it. Even though the network is pretty simple, you can throw in a bunch of like linear layers and activation functions and sort of make it a little more, make the network a little more complex as compared to how simple it is right now. And then you can actually play around with the optimizer and the cross entropy loss and, sort of see what kind of effect it has on the accuracy of the model. And yeah, I think that's pretty much it. It's a very simple, small exercise that you'll be able to quickly finish. Here at the end, we have like a bonus section for you, which is basically has like a couple of components. One is label smoothing. So label smoothing for all of you who are new to all of this, it's basically like a regularization technique which you use during the training of neural networks. And it basically involves like smoothing out the one-hot encoded target distribution of the model prediction, basically. So this helps the model from becoming very overconfident about its predictions. So I think this is a good thing to have and a good parameter to add to your cross entropy loss. It's basically like you add a small non-zero value as the label smoothing factor in your cross entropy loss. Again, which is something we would recommend playing around and experimenting with to just identify what value works best for your setup. And we also have some bonus sections on optimizers. This is where I was talking about Adam P, which is not directly available in the PyTorch documentation, but this is how you can install it and actually see how it works. And for certain kind of models, it actually gives like a good result. So we would also recommend like experimenting with this. We also have a bonus section on dropout as well as batch normalization and schedulers. So I think, yeah, if you guys haven't followed along, I would recommend like quickly finishing up the notebook. It's not going to take a lot of time, but also like maybe try to run experiments and actually like play around with it till you get comfortable. You'll actually understand the value of what I'm saying when you get to homework 1 part 2. And I would again highly recommend watching the dataset and data loader recitations, which our TAs have put together with such an effort, and it's going to really help you with your homework 1 part 2. How many of you have started homework 1 part 2 or even like looked at the write-up? Okay, that's nice. Good job. For those who have not, I think just started early. I think the earlier you start, the better it is for you. There'll be more things coming on in this semester, but just, yeah, I think you can just get started early. Are there any questions about the exercise notebook? If you guys don't have any questions, feel free to have pizza. And then you can get back and then we have you start with the bootcamp.
Maybe just making sure there's people and others in the
We are 25 minutes left, so it took 35.
Okay, so you start the bootcamp at 3:30.
This, we had an event just now.
Or do you want to start earlier?
We can even start a little later if everyone's still eating, but
So that we can inform the
I did my
people on.
military service.
yeah, do that, okay.
Yeah, so I think for everybody on Zoom, we'll be starting with the bootcamp at 3:30. So it's 15 minutes from now.
So, what's up, everyone? So, I'm here to talk about homework 1P1 with you guys. Has anyone started homework 1P1 over here? I got 1, 2, 3 doubts beforehand. Cool. All right. So, I'll just roughly go through what we're going to be doing in homework 1P1. So, you guys have a rough idea on what is expected from you guys. But essentially, I would say homework 1P1 is pretty simple. You guys don't need to worry much about it. Hopefully, let's try it. Yep.
It's okay if you started.
So basically, if no one started it, you just need to get the write-up and the handout from AutoLab. Just go to AutoLab, homework 1P1, and usually you get it from over here. In case you guys were wondering where to get the write-up and handout from. So just download them up from here. And yep, let's open it up. So this is the write-up. 38 pages, seems quite big, right? Yep,
Yeah.
even I had attention of that actually. But it's totally fine. I'm just going to go through it roughly so you guys can like at least get a brief about it. And hope you guys enjoy the pizzas as well. Because if I make some mistake in between, it covers it up somehow. Gotcha? Cool. And for the people who are online, I just sent some virtual pizzas on your way. So I hope that's cool. Yep. So let's get started. So we can go to the write-up. What's up?
I've got a question over there.
Oh,
Okay.
oh yeah. So the mic doesn't work.
Testing, is that any better? How about now? Is this any better?
That's better.
Okay,
Yeah.
yeah, it's pretty close then.
All right. So sorry if my voice is a bit too low. Never had the habit of shouting, so my bad. So when you come to the write-up, you'll see this checklist over here. Quite helpful to navigate your way through the homework. So essentially, when you're done with like few parts, it's better to just click it and see what you're done with. So let's say if I'm done with MLP with 0 hidden layers, just click it and just follow it through it. I would say that's totally fine. It's pretty simple. The size of the text, cool. Yeah. Okay, is this any better? Gotcha. So, basically, what is the P1's doing is basically you're trying to build your own PyTorch library called MyTorch. It's pretty straightforward for the homework 1P1 because those are just your building blocks essentially. And you'll be adding them as you go along with your homework. So basically, homework 1 is just your basic building blocks with your linear layers, your activation functions, your error losses, and all that stuff. But homework 2 onwards, you'll be doing something with CNNs. The homework 3, you'll be doing something with RNNs. Sounds pretty crazy, but it's totally fine. Hopefully. Yep. So this is just a small checklist. If you guys want to use it, you guys can use it. Go ahead. It'll be very helpful. If not, it's totally fine. So the first part is essentially going to be your linear layers. So let's go to our handout if I can. Yep. So basically, when you get your handout, you get this small extension in the end called .20 or whatever number comes in. My recommendation is just to rename it and remove that .20 in the end. You can extract it. Yeah, so let's say compress. Oh. Oh, my bad. So yeah, you need to remove that one also in the end. So just remove. And now you can just simply extract it. Extract files here. And I hope it's extracted somewhere. If not, then screw it. So, yep. Let's go to our linear layers initially and see how it is. Basically, most of this homework is just you converting formula to code. That's pretty much it for this homework. So over here, let's look in our handout. You just need to basically write what's given over here. So it tells you how to initialize your weights and biases with 0. So if you go to your write-up over here, essentially, and go to your linear layer, over here, you'll also be getting a table where it tells you what is your shapes for everything. So let's say for your W, basically your weight. Why does it keep going over there? Second. Yep. So when you go to your W over here, you can see your shape as like C out, comma C out into CN. So you know your shape, what is going to be over there. Based on that, you can just make your initializations, I would say. And if you look into your forward pass, yeah, it keeps going over there for some reason. So yeah, if you keep going to if you go to your forward pass, you can see the formula written over here. It's highlighted in blue. So basically, any formula that is highlighted in blue, it basically says that you have to convert that to code. So for your forward function, if you go, over here, it's written, you have to find what is self.a, self.n. It'll just tell you what it is basically on the write-up itself. And then it tells you Z. Z is basically the formula where you have to write over here. And if you look over here, it's just this formula. So you just need to basically convert this formula into code. There's nothing tough in it, at least for the homework 1. I can guarantee you that. Homework 2, I'm sorry. Yeah. So backward propagation, usually you'll be having more formulas to be done. But again, it's just converting your text to code. That's it. That's pretty much it. So if you go down, you look over here, this is the blue ones that are underlined for you. You just need to put these in your backward area in basically your code. So if I show you the backward, it's pretty laggy. Yeah. So if you go to backward, they tell you do DL by DA, self DL DW, all those basically formulas are written in the write-up for you. You just basically need to write them properly in the code form. That's it. And that's basically your linear layer done. I hope it won't take more than 20 odd minutes, 25 odd minutes, hopefully. If not, we TAs are always there to help you guys out. I'm at least there. I'm pretty sure the other TAs will also be there, especially Kate, Quentin, and Ishan, wherever he is. Yeah. So, yeah.
Just not gonna say me, okay?
Oh, sorry. I mean, you, my bad. Alex as well, my bad. Yeah. Very bad remembering the names. So that's basically a linear layers. Now we go to the activation functions. So basically activation functions, you would be having, let's say 4 scalar activation functions and 1 vector activation functions. Basically, your scalar activation function is just going to be sigmoid, ReLU, tanh, and GALU. Your vector activation function is just going to be softmax. I think the professor might have not covered it till now. If not, he will be covering it soon. But for this homework, especially, all the formulas are mostly written inside it. So that should be fine. If they are not written for it, you can just go to Google, type what's Galo's formula. I mean, Galo is there because it's a little bit complex. tanh might not be there. Relu might not be there. So you guys can find that online as well. It's very, very simple. So if I go over here and I show you, again, you get the table for it, for your basically your shapes. So you can identify what your shape is for every single thing. That's totally fine. So yeah, so if you see over here, sigmoid is written as this formula over here. You just need to convert, you just need to write this in code form, and it's pretty simple. So A is equal to 1 by 1 plus e raised to minus z. And if you go to the handout, sorry, the computer is a bit buggy over here. So let's go to activation.py. Yeah, so basically, if you see over here, they already did one for you already. Just basically, my suggestion would be Control C and Control V, followed by Control V, followed by another Control V. Do that for like literally all your activation functions. Softmax is written for you a bit because it's a little bit complicated. So at least for your, let's say, tanh, sigmoid, and Relu and Gelu, you just need to like basically paste this and just change up your self.forward area based on the code over there. So I'll just give you one small example for sigmoid. So for sigmoid, basically you get Z and you just need to write this formula over here. And that's pretty much it. So basically write A self.A is equal to something, 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 Z. I cannot give you the solution right now. Pretty sorry, but it's pretty simple. Okay. So same thing for tanh, same thing for Relu, same thing for Gelu, and you'll be sorted out in that regards. So let's go to the write-up again to show you how it is. So sigmoid's forward function, again, just one formula to be written. Backward, you just need to write this formula. Again, anything that's marked in blue, it needs to be converted to a formula. I mean, basically into code in your handout. That's it. Same thing for tanh. So basically tanh, they might have given you the forward function. Backward function, you might need to figure it out somehow. If we give you the backward function also, then the homework would be like done in like a couple of hours, I would say. So it's pretty simple. You just need to do some derivations. It's very straightforward. If not, TAs are always there. So office hours are meant to be bugging out the TAs, by the way, if anyone knows about it. Again, Relu, just find the forward function from, I would say, internet. Just write, if you want, I can just go over here. Relu activation function formula. Get it, and go to images. And it's somewhere over here. You'll get it. It's pretty straightforward. Again, nothing to be done most of the time. This seems like a straightforward way of doing it. So again, Relu, get the formula from the internet or basically from your slides, I would say. Slides are always more reliable with your formulas. If not, you get it from the internet as well. And we also give you some coding hints over here if you want. Basically, if you want to find max of something where Relu activation function you need to, just use np.maximum or np.amax, and that's fine. And similar for Relu.backward, you just need to go to, I would say, go to the slides or go to internet and just figure out what's the backward formulas for them. Pretty straightforward. Again, you get a coding hint to use np.where. So that's like a small, I would say, help in our regards. Galo is a bit more difficult to do, I would say. So again, we highlighted in blue what formula you need to use. It's this weird formula over here. I don't know if we'll be going through the formula in detail in the class, but essentially you just need to convert this to code. And over here, basically ERF is nothing but you'll find that in basically the SciPy library. Just a few you just need to look into the documentations a bit and you'll figure it out. Again, we give you the backward equation as well for Gelu because it's a little bit complicated. Just convert it to code, you'll be totally fine. Hopefully it's not going to be too difficult.
Let's go to our different section, maybe we could.
Yeah. So again, softmax, it's the only vector activation function. Again, most of the code that you need is written over here. You just need to convert it to code. I mean, you just need to convert it to code, the formulas. Backward also essentially is the same thing. Let's move on to another section. That's going to be the neural networks. Okay, so once you basically create your building blocks, your activation functions, your linear layers and all that stuff, you just need to make your MLPs in this case. So there are like, I think 3 MLPs you have to do. One is with 0 hidden layers. Again, pretty simple. I am pretty sure, yeah. So we give you the formula in hand over here. You just need to basically copy paste this into your handout. Nothing too difficult, hopefully. And again, for backward also, it's basically given to you over here as well. Just copy paste this, you'll get your answer. If I have to show you the handout, 1 second. Okay, it's funny. Yeah. Let's go to. So yeah, basically you just need to write this formula that was given in the write-up over here, especially for MLP0, and you'll basically get your answers. It's very, very straightforward. MLP1, similar thing, just there are 2 of them this time. And MLP4, we have, I would say, a loop, for loop for it to make your code more modular. Again, you just need to do it like for one time and it's done, basically. Hopefully, it will not be too tough. You should be able to do it. Again, let's go to other section. Yeah, so basically after your MLP is done, you have to get your loss functions sorted out. I think over here we're doing only 2 loss functions. One is the mean squared error and cross entropy loss. Again, just basically formula to code. I'm just repeating myself 1,000 times for the next 5-10 minutes, I guess. Just formula to code, formula to code. Yeah. So if you see the formula is given over here, the formula is given, just convert it to code. If you go to your write-up, yeah. Go to your write-up, go to my torch. Hopefully it's in the loss.py. Yeah. Yeah. So basically, if you go to your mean square error loss, they tell you what is SE. You can see in the write-up as well. SE, just write that formula over there. SSE is over here, just write the formula. MSE, that's the end formula. Just write it, you get your answer. For backward, you basically just have one formula, which is basically this bit. And if you just write that in your homework, that's pretty much it. Your MSE loss is done. Same thing with cross entropy loss. Again, just formula to code. Sorry for repeating this like 100 times because that's basically it for this homework. So hopefully nothing too tough. Homework 2, like I said, I'm not going to guarantee that. So
You should be.
that's basically your loss functions done. Now we go to optimizers. For your optimizer, we'll only be doing your stochastic gradient descent. It's not too complicated, I would say. So
just 1 second. Just it's like Hanan is here trying to make it as easy as it possible for you guys. So unlike previous semesters where the TAs have told about how difficult or hard it is, he's trying to make you all feel that it is easy and it's doable. Of course, it is harder than it he's making it look like, because your agenda is not just to complete the homework, but to try to understand everything you all are doing, right? As the semester goes, the workload is going to be very intense. So finishing the homework is essential for grades, but understanding what you're doing is essential for your learning, right? Which is what you're taking this course for. So many a times you may have to sort of balance out finishing the assignment, learning separately. So you could try to finish it first, learn later, learn about it first, finish it later. There are a bunch of strategies that you all could take. But what he is trying to focus is, if you want to finish it as soon as possible, if you are on a very tight deadline, we've sort of made it very easy for you all. But if you really want to learn and extract that knowledge, try to go through each step, try to understand why it works and how it works, because that sort of ties into the future homeworks, the bonus homeworks, and autograd as well, right? So if you just want to finish it for the sake of it, it's easy. But if you want to learn, spend some time, submit it on AutoLab, get the 100, and then just try to learn and prepare for the future homeworks as well.
Yeah. So like I said, most of this homework is just you converting formula to code. That's it. So most of these things will be taught in the lectures for you. So lecture bit is totally fine. The basically you doing the homework itself, most of the formulas are there for you written in hand. So again, for SGD, we are going to be doing it without momentum and with momentum. Basically the formulas there, code, that's it. All right. So regularization technique is the one area where you guys might have actual issue in this homework because the formulas are very, very lengthy. And to basically convert it to code, you might need to like think 5-6 times, hopefully. But if you do it properly, it's pretty straightforward. So again, you guys can have a look into the, I would say, class structures and all that stuff. It's quite helpful, I would say, to understand what the homework is. But again, if you just want to finish up the homeworks, formulas are there over here for you. That's pretty much it for the homeworks, I would say. Again, these formulas might be a little bit tricky to understand. We will not be covering them in depth because it's a little bit tough to understand the derivation bit of it. But hopefully, I would say if you implement this right, you will not be able to like, you'll not have any hard time with the homework, hopefully. And that's, yeah, I would say if you know the formulas in hand already, you just need to convert it. Homework 1 P1 is just that. Homework 2 P2 onwards, the coding gets a bit intensive. For that, you might need to really understand the concepts beforehand. But for homework 1, it's totally easy. You guys can get it done. All right. Any doubts regarding homework 1 P1? If you want to do. Yeah. Try making it look easy. If it looks tough, PTAs are always there.
Yeah.
Yeah.
That's which.
Yeah. Cool. See ya.
So no final questions about homework 1 P1, guys? This is actually kind of heavy, my gosh.
Yeah, it is.
Hanan. Mouse isn't working.
Mouse isn't working.
Oh, fish. I have to click it somewhere. Jeez. Oh, geez. All right, hey guys. So I'm going to talk about how to get started with homework 1 P2. This portion is probably going to take the most time and is likely what you guys are going to be really wanting to collaborate with your groups on, particularly because you'll be wanting to run multiple ablations. So let's begin. So yeah, we're dealing with phenome label prediction here. We'll be giving you guys an audio data set that you're going to need to write the code for, but we'll give you the data set initially. Okay, can you guys hear me better now? Okay. So yeah, we're going to be dealing with predicting phenome labels. And we're going to be doing, yeah, so what we're going to first be doing here is we're going to want to go to Kaggle. The competition Kaggle is given, and you're going to want to download it. Inside the notebook that's provided, there's automatically stuff set up. You're going to want to set up Kaggle API key to download it properly, but the code should be provided for that. You can also do it locally, of course, which might be a little more fiddly, but might be also beneficial in regards. And you're going to want to write your data set or your data loader to load data set. And yeah, as you can see, you can set hyperparameters, model architecture, LR, optimizer, scheduler, etc. You're going to want to do some testing, and you're going to want to train and test the model after that. And yeah, after you've got a model that's working pretty good, you're going to want to submit to Kaggle. Initially, we only need to cross the very low cutoff for the early submission bonus, which is going to be 55%. So you shouldn't be too worried initially. Okay, so we went to 65. Okay, 65%. 60. Okay, went with 60% this year. Yeah, so once you hit that, you'll be able to get full points for the early submission bonus. But after that, we're going to be releasing what the other cutoffs are. The medium, then the high, and the low. So yeah, the data set is in raw speech signals and speech waveforms, and we're going to use short time Fourier transforms to get them in MEL spectrograms. You won't need to worry too much about this. The technical details are included inside of the actual write-up, but in reality, you're going to be more concerned about actually making the model and coding the data loader and everything and setting it up so you actually can start. This aspect is slightly given to you guys. So here are the phenomes that we're going to be predicting on. You can see the common ones in the English language, as well as SILV or silence, SOS, start of sequence, and EOS, end of sequence. There'll be some small optimizations you can do in this regards too, depending on how it's set up. Yeah, here's an example of the audio data set that we're given. Note that you have to go over here and you have to fill out the MFC directory, transcripts dir, everything is generally not implemented. And you're going to also fill out for loop down here. All the code is going to be provided for you, but you're going to have to go through and actually fill out a large portion of the section specifically in the data loader and also the neural network, as well as, yeah, just throughout, there'll be a couple of small to-dos. So yeah, running ablations. This is probably going to be the most significant part of this and probably why you guys want to start really early. It can take a lot of time, like a lot of time if you actually want to cross high per se. And even crossing medium, suppose you have an architecture and cross medium, it may still not be initially obvious if you were able to do it. You might have the wrong learning rate or whatnot. And this is where getting a group makes a lot of sense. Then why we're doing the whole group form thing. So yeah, don't forget to submit the group form by the 29th, guys. And also maybe after this, talk to people who you might want to have in your group. You're allowed to run ablations together where you talk to people and you're like, okay, hey, run this shape of architecture. So you want someone to run like a cylinder or something, or someone to run a diamond. And doing this can get you a huge amount of information and save a lot of time. For the first homework, you might be able to scrape by without actually doing a whole ton of ablations, but this becomes greatly more relevant continuously as we go on. The second homework, for example, the second P2 took me a huge, that took me a huge amount of time to actually do ablations for, because I was taking like 12 to 18 hours of training the model just to actually get to testable state, where this one is like 2 to 3 hours, 4 hours, I was actually getting enough information. So yeah, start really early, and especially when doing ablations, because you're going to want to go for the high cutoff for full credit, you really want to communicate with your group and do it with your group. Yeah, here's an example of 1 dB logging for a group. As you can see, you have the general val loss over here, val accuracy, learning rates, train loss, and train accuracy. You really, really want to start early and you want to try to log together. And yeah, try not to be too ambitious when starting with your initial ablations. This is particularly after you guys get your very early cutoff done for the initial submission. But if you try to change the model very significantly and you're trying to get something that is like really specific, some, let's say 7-layer network with a very specific shape and very specific activation structure, you may end up getting very unreasonable results. So it makes sense just to start on something that you can experiment and augment a little each time when doing testing. Sounds basic, but it's very easy to just end up being a little too ambitious, and there you go, the whole day is wasted on training something that you end up having to discard. Yeah. Are there any general questions, by the way, on anything at all? Shoot, what's up? Complicated. So realistically, you're going to want to probably use a T4, which is the recommended GPU for this class. And on Collab Pro, you have a variety of GPUs. Technically, if you want to pour more money into it, you can use something like an A100, which should get you at least twice as fast training. It becomes pretty expensive. So I recommend just a standard high RAM setup with a T4. Anyone else have any additional questions? No. Yes. Yeah. Specific. What's the exact policy on this? It's too dark for my old eye to see. What? Yeah, they're asking for Okay, so you're allowed to collaborate for the quizzes, but you have to make individual submissions. Your work has to be your own, but you guys can talk about material with your groups.
Study groups.
Only in your study groups. Does anyone else have any additional questions or? Okay. And I'll just include this over here if anyone wants it from last year.
Yeah.
That went a lot faster. No one had any questions.
Stop recording. Should be good to go.
Jeez. I can't get the thing.
Yeah, I guess I'm thinking.